morning, everyone. I'm Steve, and I'm a Ph.D. candidate in the Department of Physical Education and Sports Sciences. Today, I would like to introduce a topic focused on data, statistical design of experiments, and sample size selection. This article is based on the Dotter and Corden in 2020. And I will dive into this topic into those sessions. And first, I will introduce the purpose of this study, and then I will also introduce the principles of experimental design. And I will also introduce the fundamentals of power analysis. Finally, we will move on to the considerations and conclusion. First of all, let me introduce the research topic of the sample size calculation. In the research context, the investigators often face a significant uncertainty regarding variability and exercises during the planning phase. That means the funding agencies and journals increasingly prioritize the rigor and reproducibility of the study. And since that the objectives of the sample size calculation is to elucidate the fundamental principles of experimental design and to introduce the concept of power analysis. And this sample size calculation also provides methodologies for sample size selection across various experimental scenarios. And the core value of the sample size calculation is that it might mitigate the risk of underpowered studies failing to detect those meaningful effects, which what I mean by that is the type 2 error. And it also can prevent the allocation of excessive resources and address ethical concerns regarding subject exposure. To begin with that concept, we draw in from the Fisher's fundamental work, which is the robust experimental design relies on several key tenets. And those concepts, Dr. has also introduced those concepts. That is the 3R, right? The first one is the replication, which means the single observation is unreliable due to natural variability. And repeating the experiment allows for estimation of experimental error and enhances the reliability of those results. And the randomization is a kind of allocation of treatments to experimental units. That is also very imperative for the robust results. So the objective is to ensure that unspecified disturbance, for example, like those edges or disease severity, might be distributed equitably across those treatment groups. It can also prevent the confounding of treatment effects with uncontrolled variables. And the third one is the blocking concept, the grouping homogeneous units into those different kind of blocks. For example, you might have different kind of blocks like the eye of the same object, and we can also divide into those different kind of subject like the within subject design using the fellow eye as a control. And those benefits including those removes larger the subject variability and thereby increasing the precision of those comparisons. And the last one is a modified design. It can avoid the inefficient one factor at a time approach, and verifying factors simultaneously allows for assessment of interaction effects. So since that we have known the main purpose of the sample size calculation, now we have to dive into those 4 components of power analysis. Those 4 components prior to the experimentation for critical parameters must be defined. The first one is the significant level, which we also call the alpha. And that is the probability of rejecting a true null hypothesis we also know it as the type 1 error. It's typically set at 0.05. And the second parameter is the statistical power, which is also known as the 1 minus beta. It's the probability of correctly rejecting a forced null hypothesis. A minimum threshold of 80% is a standard convention. And the third concept is the effect size, which is the delta. That is the magnitude of differences considered scientifically or clinically meaningful. For example, 0.5 mmHg reduction in low blood pressure. And the last one is the variability, which is also known as the sigma. That is the standard deviation of the outcome measure. It derived from the prior data or the prior literature. So when we consider those different kind of concepts or parameters, we have to know that the hypothesis testing outcomes, usually we can divide that into 4 blocks. And we can see from this figure, from the left side is the null hypothesis is true, and the lower one is the null hypothesis is false. And we can also see from the axis, and that is the accept the null or reject the null. So it seems that we can have 4 kind of hypothesis outcomes. In those different kinds of outcomes, there are 2 potential errors. The first one is the type 1 error, which means it rejects a true null hypothesis. And the second kind of error is the type 2 error. It means that you accept a false null hypothesis. And we can also conclude from that kind of hypothesis outcome into the definition of power. So what is the power? Power is a kind of probability that you can correctly reject the null hypothesis. So we can see from this figure, from the left side to the right side, and we can see the distribution of different kind of hypothesis testing, and we can see from this figure to understand the definition of power. So it seems that the definition of power is a kind of probability of correctly rejecting a false null hypothesis. And there are some kind of interrelationship among those parameters, that is the power, effect size, variance, and the hypothesis testing. We can actually conclude from those figures above, and we can conclude those different kind of observation. That is, when the power is elevated, the sample size might be also elevated. And when the effect size is slowing down, the sample size is elevated. And you can detecting subtle differences require more data. Actually, we can see from this figure, it provides more comprehensive understanding of those concepts. And we can actually observe from those figures, that is the interrelationship of the sample sizes, effect size, and power. When we try to elevate our effect size or power of each study, the sample size is very important and pivotal. When we have more sample size, usually the power and the effect size will be more. And in the following session, we will try to divide each kind of study design into different kind of scenario. The first one is the one sample mean test. And the context that we try to test whether an intervention reduces the mean from a known standard value. And the formula is like this, and there is a application scenario trying to use in those pair comparisons. And the second scenario is that we're trying to compare two independent means. In the context is we try to compare means of two independent groups. For example, like the very classical treatment versus the placebo. And we can have that kind of hypothesis like this. And the sample size calculation formula is like that. And we can also have different kind of variation of those different kind of sample size calculation formula. Seems that we also have those practical consideration of the non-parametric test and iteration. In the practical experimental design, the iteration rate is very important. Since that all the participants might not be able to join your experiment all the time, they or he might drop out during the experiment. So it's very important to anticipate the iteration rate. So let's move on to the conclusion part. Since the robust experimental design, for example, like the randomization and blocking of those design, it can minimize the biases and variance. The power analysis must be conducted as a priority to ensure the feasibility, and the sample size determination is not merely for grand compliance, but is truly very essential for those scientific integrity. So there are some kind of software like the G-Power or R and any other kind of software. And I also do some R simulation study for those sample size calculation. So I will also provide you guys those data and the data set. That's all.